we went along, I just kept talking about things that I knew from past experience. And he said, "Oh, you could give a talk about this." So I did. I am. So, what are the Eastern Anthracite fields? It's participatory. I'm not just going to stand here. They're the fields where you grow anthracite, right? Or maybe the ancient Anthracitians grew their crops there. All right, so anthracite is a type of coal. See there? It's the highest ranked coal, the percentage of carbon. It's usually like, the numbers vary on how they define it, but 88% to 97% carbon. This was originally plant matter. It's been compressed and formed coal. Because it's been very well compressed and heated up to 400, 600 degrees centigrade, or miles below the earth, at least 2 miles. That's why it's anthracite. Anthracite is a relatively rare type of coal. It's hard coal, known as stone coal. It's a high heat, low dust, and ash, but it's very brittle and it will fragment easily. It's difficult to get started burning, but once it starts, it burns. And it does not go out. It's located in thin veins throughout this anthracite region. 10 inches of peat would be compressed to 1 inch of coal. So if you look at all the coal, I think the highest spot is up near Tamaqua in Pennsylvania. They have 141 feet of coal in different veins under the ground. So that was 1,400 feet, a quarter mile of peat. So these swamps that it grew in were extensive. And eastern Pennsylvania has the largest anthracite fields in the world. It's almost half the anthracite, and only about 1/3 of it has been taken out of the ground. Here's some pictures of anthracite coal. They're not the greatest because anthracite coal is a black rock. It's glossy. Almost looks like jet or something. It's very lightweight for a rock. It has some texture to it, but not a lot. One of the churches up in Shamokin, the miners actually mined a big block of anthracite, and they made the altar of the church out of anthracite because it's hard. When you get a piece that's real fine, it has no layers in it or anything, and you can carve it. And it's kind of unique in that way. Here are the eastern anthracite fields, those pink fields up there. The rest of the fields in yellow are bituminous. That's a softer coal. That's probably 80 to 88% carbon. Then it goes down to subbituminous and lignite, and then peat. So as you get less and less coal in it, less and less carbon in it. It's not been compressed as much, and that's the main difference. It was formed at the same time. These are Carboniferous coal fields. Right up above the, maybe I should do this up here. If I can get up in here is the Pennsylvania oil region. So you hear about Quaker State Oil and all that. So there's some interesting state parks up there too for looking at oil if you get into this kind of stuff. What do we know about the Carboniferous period? Since you didn't know what the anthracite fields were, come on. What do we know? Bird fossils. Are there? Okay. George. Okay, so George says, depending on where you are in the world, Carboniferous is actually 2 periods. And yes and no, and we'll get to that in a minute. In North America, we usually separate it into the Mississippian and Pennsylvania periods. The International Standard of Geological Classifier, stratigraphy, I think is what they call it. They define it as 1 period, the Carboniferous, but we divide it in 2 here. It's 360 to 299 million years, the total period. About the first 2/3 of that is the Mississippian. It's named the Mississippian because in North America, the fossils that you find are marine fossils in the Mississippi Valley. So the famous crinoids of Crawford County, Indiana. There's some beautiful fossils from there. They're Mississippian in age. And then in eastern U.S., the coal is, and that formed mainly later, although some of it did form in the Mississippian too. First forests formed some 25 million years before the Carboniferous. So when we start talking about 360 million years ago, or 385 when the first forest, plants have not been on land that long. And we'll get into that a little more. The Earth's continents looked very different. The climate and the atmospheric composition were different. Land animals were arthropods, which like insects, arachnids, scorpions, centipedes or millipedes, and amphibians, because the amphibians had come to land. They came out in the Devonian tetrapods. And in the middle of the Carboniferous, there was this evolutionary revolution, or I don't know, you can't call it an invention, but change where we came up with the amniotic egg. And so the amniotic egg has a layer around it, a membrane that maintains the moisture inside. And so the egg does not have to be in some place that's always soaking wet, whereas the amphibian eggs always did, and all fish eggs and all that. The Appalachian Mountains were off the east coast of the United States, out where the ocean would be, but the Iapetus, I'm not quite sure how to pronounce it, the pre-Atlantic Ocean that was there had closed. It was closing at this time. It's known as the Age of Coal. It had one of the highest oxygen levels of any time in Earth's history. Okay, and the oxygen percent now is like 21%. During this period, it was up as high as over 30, some estimates as high as 35%. At 40%, almost anything will burn, when that oxygen is that high. And although the Carboniferous is the remains of swamps, there are fires, obvious fire scars in some of the fossils, so that even though it was a swamp, it was still burning because the oxygen was so high, oxygen concentration. Okay. The pre-Carboniferous, the Devonian, plants originated in the ocean and had come out onto land. They may have come out a little bit earlier than this, but they were very low-growing, basically slimy or on the ground or with no real structure to lift them up. And so to overcome the differences as they came out on land, they had to develop support structures to hold them up. They had to conserve moisture, had to be able to transport water and nutrients up from their roots if they grew to any height at all. They had to be able to withstand direct sunlight. When you're in the water, you're more protected. They had to withstand greater temperature changes and ranges because, again, the water moderates that stuff. And then you have a gas exchange with an atmosphere instead of in the ocean where it could just diffuse right out of the leaves simply. Then we go to the Carboniferous, and this is what we're going to be talking about. Here's a picture. It has your mandatory large dragonfly. Dragonflies had wingspans up to 2 feet. So each wing a 2 foot on either side, right? Pretty massive. You could do that because the oxygen was so high. Insects breathe through their skin, through little tubes through their skin, spiracles. And the oxygen could diffuse into a large insect like that. Here you don't see much water, but you do see a multi-layered forest. I like this picture a little bit better. It shows a lot more water. You see the different layers there, and you start to get an idea. Some of these trees always look to me like something out of Dr. Seuss, they're just weird looking trees, but there are reasons for that, and we'll talk about some of those. Upland forests during this time, but they were not nearly as well preserved in the fossil record. It's because they were dry, they weren't covered up, they didn't, they just decayed. One of the reasons people think some of the Carboniferous plants stayed around so long is they had just developed lignite. And lignite is something that makes them a little stiffer. And so plants have just developed that, and they're not sure whether either funguses and bacteria were not good at breaking it down at this point yet, or whether maybe just the moist content in the swamps prevented the breakdown of the lignite. Okay. So here is the Earth at the early Pennsylvanian. This slide is from a tool called from the Howard Hughes Medical Institutes called Earth Viewer. It's a real nice tool. You can slide that little slider up and down. Over here, this slider up and down, look at different periods. You can play it so it just plays through and moves it through. You can turn the Earth around, look at different aspects of it. But if you look at it, you can see here's the equator, runs right through the Great Lakes. We're south of the equator. Here's the eastern Pennsylvania fields right here. So maybe 20 degrees south, but still tropical. You can see over here, you've got Spain, you've got Great Britain, Scandinavia. Up here, you've got Greenland. Down here, you have the tip of Gondwana, which was a large continent, the big southern continent. That is Africa, and South America is down here. You do not see the inland seas here. And that's kind of disappointing to me because in the Pennsylvanian, throughout both the Mississippian and the Pennsylvanian, these seas would come in and go out. Most of Gondwana was down around the South Pole. So when we went through glacial cycles, the glaciers formed on land, the sea levels dropped. Sea levels dropped, they left these big flat plains, great for coal swamps. Then the climate altered a little bit. There's a set of cycles called the Milankovitch cycles, which involve the eccentricity of the Earth, how out of round it is, the tilt of the Earth's axis, the wobble of the rotation, and they form a cycle that brings in ice ages and lets them go again. Right now we're in an interglacial period. We'll probably have another glacier coming. I mean, it's going to be thousands, tens of thousands of years maybe, but it will happen. So throughout the Carboniferous, this happened, and these seas would go out and come in. They would cover up the swamps and destroy the swamps. As you can see, there had been an ocean here. It's called the Phaeatus Ocean because Phaeatus is the father of Atlas, who is the Atlantic Ocean is named after. It's kind of strange when you see all these classical mythology references in biology and geology and stuff, but I like it. It's kind of neat. And as you can see, here we are in Pennsylvania, and the mountains are off the coast of what now is the East Coast, which will be running right here. Here's Maine up here. We're coming down. We get down to North Carolina, get into Florida, and got mushed up there because the land mass has been corrupted. It's no longer the same piece of land. Those mountains were off the coast. And what's going to happen is land masses are going to still coming together. They're forming Pangea. So that it's all land, this huge continent. And as it does, those mountains that are in what had been the ocean are going to be pushed over on top of the swamps and form the Appalachians. And this is the last major mountain building period we had in this area. Okay, so quick look at the atmosphere. If you look at the beginning at the bottom, get down here, started out at about 20, maybe 19% oxygen. This as it goes up to 29. Like I said, I've seen other references that say it was higher than that. we look at the carbon dioxide, it started at maybe 6%, and it went down close to what it is today. It should be closer to zero than that. So what you had was all these swamps growing. Swamps naturally take up, trees naturally take up carbon. Boom, goes into the ground, into the swamps, gets buried, pushed down. It's not available anymore. All that carbon dioxide disappears. Everybody's familiar now with the greenhouse effect. As that carbon dioxide went away, the temperature starts to drop. It drops more and more and more. And so this caused an event called the Carboniferous rainforest collapse. For some reason, they have an extinction event here at 318 million years. I wasn't able to find out exactly where that is. Most places put the Carboniferous rainforest collapse probably around 305 million years ago, so a little bit later than this. And what happened was it got cooler. As it gets cooler, there's less moisture in the atmosphere. The oceans are not evaporating as much because they're cooler. We also have all these land masses together, so there's not as much coastline. Less coastline means less chance for moisture to get into the land. And so all those things had an effect there, change the climate. So why I collect Carboniferous fossils? Because they're awesome. And I'm hoping you're going to get that feel as today we go through this. I hope you're already there. They remind me of my youth. No, I was not around during the Carboniferous. But I grew up in North Jersey. The area I grew up in had all been logged. And there were rock crusher mines up behind my house where we go play in the woods. And so there were big open faces and piles of spoil and haul roads through there. And when you go up into an old strip mine, you find the same kinds of things. It's about the same latitude as where I grew up till I was about 12, and it just feels like home to me. I love the area. I like to explore the old strip mines. You never know what you're going to find. You can walk along and all of a sudden, boom, there's this big drop off or huge spoil pile, and you think, I bet there's a billion fossils in there. There's good fossils. It's close to home. It's only 2.5 hours up the road, southern parts. It's also something that you can kind of understand. There's a lot of history there, the technology of mining. The more I get into it, I've been through museums and stuff up there. I've read a lot about it, and you just start to get a feel for it. It just, to me, it like I say, it kind of feels like home. My ancestry is Irish. An awful lot of the early miners were Irish. My case, my ancestors stopped in New Jersey. They were servants to the wealthy people there who worked in New York. But had they not had that opportunity, there's a good chance I would have grown up out here. And then the miners changed. The Irish became too troublesome, the Molly Maguires, and a lot of labor unrest. Pinkertons got started kind of to put down the unrest of the labor in the coal fields. And they went into Poles and Slavs and Ukrainians and Italians and all different ethnic groups. If you drive through this area now, you will see the Ukrainian Catholic Church, the Polish Catholic Church, and that's how they're labeled. And because those ethnic groups each have their own church, they tend to be Catholic. And if you've never been in a coal mine, you're missing something. I know of 3 coal mines up there that you can tour. In Ashland, Pennsylvania, right up by Centralia, there's the Pioneer Tunnel. You can go in that, and they got tours of it. In up by Jim Thorpe, there's a little town called Lansford. There's a number 9 mine there. Again, you can go into that mine. They've got a nice museum outside of kind of life in the early 1900s. It's not too well curated, but it's a tremendous collection of stuff and just fascinating to watch it while you're waiting for your tour to begin. Mines, the shaft goes straight into the mountain. And I guess I should talk a little bit about that for a second, because this was coal swamps. Swamps are level. You can't have a swamp on a hill because the water drains out of it. But when the mountains got pushed up and everything got folded around, we now have mountains there. And so a lot of the coal seams were run up at 60, 70, 80 degrees to horizontal. So they're almost vertical. And it's very interesting. Other mine I didn't mention is the Lackawanna mine in Scranton, Pennsylvania. Great tour there, great museum. It's very well done. I think Pennsylvania State runs that one, and it's really nice. So if you haven't been in a coal mine, this is what one looks like. This is my favorite mine, up outside of Shamokin. This is the Bear Valley Mine. Basically what this rock face is the base of the coal layer. They stripped off everything on top of it, and then there was the coal, and here it is. If you look back here, you can see a very thin coal layer right in here. Okay, so that's a syncline where the rock dips down. There's a thin coal layer. It just wasn't worth stripping all that out because that's only a couple of feet thick, or probably a foot and a half thick. But this face here coming down behind, well, let's start with this. This is called the whaleback. It's just a big sausage-shaped hill running down the center of this mine. It's about 50 feet from the bottom here up to the top. You go over the top, it drops down about 40 feet on the back, and then boom, it's 200 feet up here. And this is where the coal was laying. So the coal laid over top of this, went down, goes about, I don't know, about 50, 60 feet, then starts up again, and boom, goes up for 200 feet. And that's how it's been smashed around. Started as a flat layer and just got bent around. While this was getting pushed up, at the end of it, which really would be about right here, it's a little off center, but you've got this being pushed down. And you start to see the geology at work. There's 5 different kinds of faults supposedly in this mine. And I'm not a geologist, but it just fascinates me. Okay, so and now let's see a couple of fossils out of that mine. Here's one. This is a sigillaria impression. We'll talk about those in detail a little bit. But it's about 2 foot across. That's my hammer. This big kind of reddish blob here is a siderite concretion. It's an iron carbonate. And in some places, they look like huge cannonballs. They're anywhere from 8 inches to the small ones up to about 4 feet, the big ones. They're just dotted in the sides of this hill. And it's just like, how did that ever happen? And there's a lot of geological discussion about that, how it happened and when it happened. Did it happen when the fossils were being, in the swamps, or was it long afterwards? And I would say just the way the fossil runs through that, it would look to me like it happened early on when the fossils were being laid down. This is my very favorite fossil. Unfortunately, it's uncollectible because that rock is brittle as heck and it just shatters to pieces. This is a eulodendron. So you've got, these are leaf scars. There'd be the big compound leaf branches coming out this. This thing runs about 30 feet across that north wall that you saw, that big high face, or south wall, I guess it is, the south face. And there it is, just with these row after row of leaf scars. And so you see this tree that was, you can see 30 feet of it, but it's hardly tapering at all in that 30 feet. It's an amazing kind of thing. And I would love to get a piece of it, but if you tried to break it out, you would just destroy it and let other people enjoy it. Below it is, and here is sigillaria again. We'll talk about that. So before we get into fossils, let's do a quick talk about study of Carboniferous fossils. They were funded to understand the geology of coal because coal was big money back in the 1800s, early 1900s even. Much of the work was done and published by state geological societies. There are papers out there, or books of the fauna and flora. There's a guy named Leo Levasque, which I'm probably pronouncing it wrong because it looks like it's a French name. He published the description of the coal flora and the Carboniferous formations of Pennsylvania and throughout the United States in 1880. West Virginia has a similar book. And these books have diagram after diagram of all the different fossils that he could get a hold of. And since he was allowed to go in mines because he was part of the state geological geological survey, they have all kinds of fossils. It's just amazing. One of the interesting things is that they found fossils disassociated from each other. So in a tree, you would find the roots, you would find the trunk, you'd find the branches and the leaves, and they may all be disassociated, and they didn't know they went together. So they gave them all separate names. So as we go through this, we'll talk about some more of that. You'll see some of those. A lot of the names have been reworked and reclassified. Some haven't. Swamp plants are the major fossil from this area. There were upland forests, but they didn't get preserved nearly as well. And there's a unique thing in coal is there are things called coal balls, which are carbonaceous concretions. And it's just a little ball of high carbonate content. And any little pieces of plant matter that got stuck in that, these formed in the swamp, does not get crushed and mangled. When you look at a piece of coal today, you will not see a single piece of plant matter in there. I mean, you just can't see it. It's gone. It's practically pure carbon. But inside these coal balls, you can actually see the cell walls and the structures, and they would section them and then do an acetate peel to peel off the carbon, and then dissolve a little more with acid to get down to get the carbonate out of the way, the calcium carbonate, peel off another layer of carbon. So it's really kind of a fascinating process, but we know a lot about carboniferous plants due to this, a lot of the very details. So here's an old diagram, the kinds of plants we're going to be studying or we're going to be visiting. First one is Lycopodium. I have a sample here, which you probably can't see at home at all, but maybe if I hold it up there, you can see it a little bit. It is upside down. So if you look at it, this is ground cedar, it's usually called, and I got some spores coming off it there. Spores were once used for the flash powder. When they took pictures of the old times, you see the movie goes, psh, that was these spores they collected for that. If you look at it close, you see everything divides into two pieces. Even the spore thing, it's two pieces. And so it's a dichotomous branching throughout. These grow up to, they might grow a foot and a half long before they re-root, but not much more than 6-8 inches tall. There's also some ground pine, which is another Lycopodium that exists today, but that's how big they get today. This is a primary plant of the coal deposits. They were a lot bigger then. Very fast growing, grew up to 100, 150 feet, 6 or 7 feet in diameter. They reproduced by spores. The trunk was straight with branches at the top. Let's see if I can go back here. You don't see a good one here without branching. You see some of these over here. Let me get some of these here. They would be immature. They haven't branched yet. And so they have these longer leaves because they don't have the top. And then at the top, when they start to branch, they get a more needle-like leaf. And then you can see on the end, there's these different sporangia cones to hold the spores. And on this tree, it's a little bit different. But again, the sporangia are down here. The main support was the bark of the tree. They were not woody. They did have a central core of wood, but it was very small, and it was mainly to carry water, the xylem. And they would often only have one single reproductive cycle in their life. So these trees grew amazingly fast. So you could have a 100, 120 foot tall tree, could grow, some people have estimated in the single digits years up to 30 years old, but no older than that. and then they would reproduce and die. Very rarely do they fall and pull the roots out when they fall. They break off at the bottom because this trunk was mainly pithy in the middle and had this outside bark that was the main structure. There's two major groups. Lepidodendron, they're called the scale trees, and we'll see why. They were dominantly growing in water-covered areas and sigillaria, which grew on land, but still like the wet areas. So here's a lepidodendron. It's got diamond-shaped leaf scars. This is probably the male half of it, the actual, what the plant would have looked like. Or is that the fossil? That's what the fossil would look like, the imprint. And this is just the mating half that was molded off of it. So they have these diamond-shaped scars. Inside there's a vascular bundle. You can look at that, and there's one for the water, and there's two air tubes because they brought air from the leaves back into the trunk. The trunks were green and would photosynthesize. Here's another one. You could start to see where they get the name scale because they look like they're covered with scales. Here's a branch. Most of the time when they branch, both branches are about the same size. There's a beautiful little one. I got both halves of that laying out over here. You can look at it afterwards, but you can see the scales. You can see the branching. Actually, the branch is here, and this part was not fossilized. I think this smaller one is a totally different piece of wood that fell on top of it because it's not the same size. It's scaling is different stuff. So it's probably not a branch. Here's a bigger one. Those scales are starting to get, not quite an inch long. They do get maybe a little over an inch and always longer, taller than they are wide. Here is a filled in impression. And so this is the mold that came out of it, but it's just kind of neat because it has all these raised little bumps. And that's probably what the plant would have looked like with those bumps being leaf scars. A leaf scar is where the leaf attached to the trunk. Now, if they're wider than they are tall, then they fall into the Lepidophyllous category. These are less common, but the trunk of the tree would be running this way as it went up. And you can see these are wider than they are tall. There's a little bit different. You can also kind of see that they're arranged in spirals, much like the scales on a pine cone or a pineapple or whatever. We'll get to that in a minute. First, let's talk about the cones. So I've got these samples out here too. They're not the greatest pictures, but you could see a cone here. It's going to be cut off a little bit there, but it was probably 2.5 inches long. Here's a slightly bigger one, about 3 inches. And these cones would hang down, and it's very interesting. I read a lot about this, and I'm not sure I understand it yet because every time you read something that's fairly technical, it's about a particular species. And different species seem to be quite different. Some of these cones had developed male spores and female spores, megaspores and microspores. So the female spores would form closer to the tree. The male spores would form out on the end. Others, they form totally different, where only the female spores would form in the cone, and the male spores were totally separated. The interesting thing about these, and the idea of male and female spores, I never really heard that before. And so I started to read up about it, and it got a little confusing, but they are actually male and female, and they have to join. So these cones would drop and fall into the water. And when they did, here's a male spore, and this is it's kind of a leaf with a spore case on the bottom. So here you can see the leaf, the main vein down the center, and then this piece here sticks up a little bit, probably would have stuck up more in actual life. And that's the male spore case. So the microspores would come out. These would all drop in the water. That's how it would be fertilized. And the lepidodendron had to grow so that its cones could drop in the water in order for it to reproduce. And they weren't going to get fertilized, and they weren't going to grow. Oh, yeah, we'll get to the question about the foliage. I think I have pictures later on. Sigillaria is the other major tree of this time. It grew in drier areas. It doesn't have those big leaf scars. It's kind of boring in a way. Got one of these over there. This is a very typical piece. You can see the ridges. The ridges would be vascular bundles that are running up to carry water up to the leaves. It again grew up, bifurcated because it's still one of the club mosses, the lycopodiums, and then it would again branch again and again. This one often had two branches and then puffs on the end of it. It was really a Dr. Seuss looking tree. Here's the impression of Sigillaria. It would fall into probably the dirt at the bottom of the swamp and the peat, or get covered up. And you would get these, they almost look like tire tracks. And sometimes you'll see them that go on for, 10 feet or 20 feet. And they crisscross at different angles. And you think, what was that? What was going on there? But these are just where the trunk fell down and impressed itself. Some of these, they actually get what's called debraded, which means the outer bark is worn away and all you get left is the vascular bundle. So you see these rows of vascular bundles in there. And this was fairly common in certain species. You'll find these a lot. You can find multiple rows of the bundle scars, or this one has a single row, more like the eulodendron we looked at earlier. And there's an impression. So the little bit finer ribs. They're only about a ½ inch apart, where the others were maybe 3/4. And if you see all these little specks in here, these specks are coal. So that's where the original tree was lying down, got compressed and coalified. Most of it is chipped away, but there are a few little pieces still adhering. To me, it's kind of fascinating just to see what you can learn by doing this. So we've got the cones, which we call lepidostroba. We've got the trunk, which is the lepidodendron or sigillaria, depending. And now we've got the roots, which we call stigmaria, because they didn't associate the roots with the tree. They didn't know what they were. Either the sigillaria or the lepidodendron had this very similar roots. And I don't think even the experts can tell them apart. If you look at them, they have these little dimples, a little spot in the middle. And that's where a rootlet would come off. So this is the main root, or a bit larger root, and the rootlet would come off. Oftentimes these are not as compressed as most of the other fossils you find in the swamps are. So check how I'm doing on time. Stigmaria again. That one's both sides. You can pick it up and look at it. Again, you can see the spiral pattern of the rootlets coming off. Here's one where you see the impression. Let me do it this way. The impression of the stigmaria, and these are the actual fossils of the rootlets. The rootlets must have been very, very fine and thin, no structure to them, got flattened right out. All I ever see is these little ribbons like this. And that's available to look at over there. After we get done that, we'll move on to the horsetail groups. Horsetails, again, something that exists today. Equisetum, you've probably seen it if you live near a stream or anything, sometimes called scouring rushes. We've got a little cone up here on the end, which would be the spores. There's a very different kind, which I picked a couple of days ago and has not lasted too well. But if you look at it, you will see it comes up, it has a node. At the node, there are branches coming off. Put it in the light. But you can look at that closer. I'll put that over with the fossils there when we get in. So again, horsetails still exist today. Calamites, which are the fossils that we have from there, are near the base of this evolutionary tree. Horsetails, the ecosystem's come much later. It was a conical tree, sometimes a bushy tree, sometimes more columnar, that grew up to about 65 foot tall. Most of them seem to have leaves, but some did not, like these horsetail today. They grew in very wet soils to substantially drier soils. And the trunk was segmented into nodes, like bamboo is. And if you look at the horsetail and you look at the fossils, you'll see that. At the nodes, there's often a radiated whorl of branches that come off. And the whorls of leaves, if they have a little collar on them, they're called annularia. If they just come right out of the node, they're called asterophyllites or astrolaria. So you can see that a little better up there. Okay. You can see the fine striations here. Those would be the ribs on it going up. And then you can see the nodes here and here. And I'm not very good at drawing this, but you can see the nodes or the nodes. When you look at calamites, if you're trying to get down to a species level, you want to look at how wide those little ribs are, how far apart the nodes are, and what the nodes look like. Some nodes zigzag up on every other rib. So it's up and down, up and down. Others, it's just like a line, sometimes a double line. I've got one in here, I think, that has a different shape. Here's a calamites pop out. You can pick that up and look at it when you look at the specimens. It's got both sides, but again, fairly fine little ridges on it. And you can see a node there, what, every inch and a half or something. Oh, that does show up better there. Okay. This is called the peacock calamites. And it's not got anything to do with the species. You can get peacock coal, you can get peacock rocks, but when this rock was compressed and heated up, and mainly the heat, I think, it would kind of like you see the sheen of oil, but it stays there. And I always thought when I found one of these, oh, it must have just split open. It's going to go away as it, the volatiles evaporate. But no, they don't. And sometimes you'll get coal beds that are littered with this, and the coal, it gives off, depending on the way you hold it, different colors and shades. The gold is very popular, and the blue, quite a few shades in there. One of the coal beds up in St. Clair is known as the peacock vein, just because the coal in it looks like this. Got those colors. Here's a calamites and an impression. That bottom is the calamites. It's about 24 inches long. You can see a node here, a node here, a node here, and there's the impression from the rock it came out of. And that's about 4 inches wide. Here's one a little wider. And this is just a large calamites. One thing that I find interesting about this, you can see the branch scars at the node. Here's one here. You go down to the next node, and they're rotated 60 degrees because it has 3 around. So the next ones are 60 degrees, so the branches are not above each other. And that, if you look at the striations, are a little bit bigger. Here's another one that's just nice color on it. And I am not sure where the color comes from, whether that's the material of the fossil or not. But I always love it when the fossil is contrasting to the background rock. Here's a little tiny thin one. But yet it goes on, and it's got all those little nodes you can see in there. Annularia are the whorls of branches on the fine stalks of these, the leaves, if you will. They're needle-like leaves. Some of them, like this one here, it's a little more rounded and oval shaped. Others are very needle-like. It would grow with the stalk here. And then at every node, there'd be a whorl of these branches getting smaller as you got further out. And so they're just the leaves of the calamites. And again, because they found them and they didn't know that they went together, they gave them a separate name. And annularia, you can kind of see a thickening here, which is that little disc around the node where the leaves came out of. Here is a calamites if you came up through the layer so it didn't get smashed flat. So it's practically round, hollow in the middle, and it's just got that little ribbed skin on it. And if you look at these and you look at the cut end of them, you can see that they basically are hollow little ribbed things. That would be, yeah, it was coming up through the layers and it just got cut off a cross section. Now, some people have used this to say, you know, the calamites fossil might not be the outside at all. It might be that inner hollow tube that got filled in. Question about that is, we think that the nodes were solid inside, that it went all the way across, so it's not likely it would have all filled in. But this specimen over here kind of gives you the impression that that might be. Calamites grew, they had spores, but they mainly reproduced by rhizomes, underground stems. So the rhizome would grow over and then it would come up out of the ground. And so here again, it was growing over, came up through the layers of dirt, and it's got a shape. Maybe it's just starting to grow, or maybe that's an internal mold again. And, you know, that's as far as it filled. A little hard to tell. So the consensus seems to be that they're the outside of the plant. And this is probably a larger rhizome. Again, that's about 15 inches long. And then it starts to turn up. That's the only explanation I can give for that curve in it, since the trees grew straight. So I think that was a rhizome growing into a tree. That's your annularia. Next, we get to ferns and seed ferns. So ferns, tree ferns, and seed ferns. Tree ferns are a type of fern. The Pteridophyta is the classification. They reproduce with spores, but a tree fern, the roots kind of come up out of the ground and the fronds don't come out till above the ground. Tree ferns exist today. They existed at this time. Most of the ferns you find, fossil ferns, are tree ferns, if they're ferns. Seed ferns are something totally different. Again, they're pteridospermatophytes. So it's fern, seed, plants. This is probably a polyphyletic group in that they didn't have a single ancestor. Nobody's quite sure how these went. They evolved in the late Devonian, just before the Carboniferous, and they decreased tremendously as we went into the Permian. The few people that feel they have found them later on, you know, even in the Eocene and things like that, but there's no continuous fossil record once you get past the Permian. They have seeds. The seeds can be very large. Most of the ferns you will find tend to be seed ferns when you look at fossils from this Carboniferous Anthracite fields, but not all of them. They grew on land. They formed an understory, obviously 6 to 20 foot tall. Long pinnules from a short trunk, which is really the root on the tree ferns, and the seed ferns tended to be the same kind of way. A stem and then these long pinnules. Pinnule would be the ferny leaf that you think, with all the little branches on it, all the little leaflets. And some of those could be 6 to 8 foot long. So here, there's two major groupings of them, and these are grouped by leaf form. They're not phylogenetic or how they are actually linked through ancestry or relatedness genetically. They are the Neuropterus, in which the pinnules, the little leaflets, have stems individual off the main vein, the pinna of the fern. usually the mid vein does not go to the end of the leaf, and it branches out into very fine veinlets or subveins, whatever you want to call them. Most of the Neuropterus are seed ferns. Now the Picopterus is the other one, and the pinnules, the small leaves, attach directly to the main stem. If you'd like more about this, I recommend you go to fossilguy.com and look up its guide to Pennsylvania plants. He's got some very good explanations of this and pictures and all. And the veins are at a higher angle to the mid vein. They come off near 90 degrees. And these are often tree ferns, but they can be seed ferns too. And then there's another one, Sphenopterus, just threw in there because it has lobed leaves rather than separate little pinnules. Animals are fairly rare. It's not that they didn't exist. There were insects, amphibians, reptiles were just starting in the Pennsylvania. They were proto-reptiles. But the insects are fairly rare. I think they must have been either consumed or decayed. There are places, not in the anthracite fields, but where they have found amphibian reptile type animals in the base of hollow trees. So a tree would fall off, would break off, and there would be this hollow stem sticking up, and there would be a little nest or a little place where the animals would would hide out and live. There are very few animals found though in here. I have never found one. I'd love to find, a single 1 foot long dragonfly wing. I mean, it'd be, I don't know what I'd do. Okay, here's a small Picopterus. You can see that the leaves attach directly to the stem. There's no little stem on them. These are very small, about a ½ inch wide at the widest on these. This one, okay, you can kind of see it. You can see it in the other sample, but these are double branched. So here the main pinna would be in here, and then it would have coming off at a branch and all these little leaflets coming off of it. So that's a Picopterus too. These tend to be rarer in the fossils that I have found, but they certainly are there. Here's one much longer. Notice how little taper there is on this long fern. One of the things, if you look at ferns today, you can classify them kind of by their shape a lot of times. Some start narrow, get wide, and get narrow again. Others are taper in one direction. Others stay narrow like this. I assume these would all be different species also when they have different shapes like that. This is Aletheopterus. This is a Picopterus. The ferns the leaflets attach directly to the stem. You can see them in here. And it's a very common fern. It kind of shows this curve here. Is that like a fiddlehead on rolling or something? Who knows, or whether that's just it fell over after dying or being washed over. And that's the shape it took up. This is a St. Clair Aletheopterus. I also have a large plate up here. Sorry about the people at home, can't see it, but a number of leaves there. St. Clair is world famous because the leaves are coated with this white material. It's called pyrophyllite. And there are two theories about what it is. The fern would fall, would make an impression in the substrate. This isn't in the coal, this is in the shale. And that impression would, as the fern rotted away or disappeared, would get replaced. It could be replaced by iron pyrite. This is the one theory. And then at some later point, this pyrophyllite came in. Pyrophyllite. Get back here in my notes to make sure I say it right. There were definitely mollusks. Whether or not there were land mollusks, I think there were, but there are marine mollusks in some of the beds further west towards Pittsburgh in that area. So the bituminous coal, the seas seem to come up more there. I have never found any mollusks or any signs of marine animals in the actual beds, but there are around the beds these the different shale layers. The Mahantango is all up around that area too, so there's a lot of marine stuff there. So let me get back to this. There was, we thought was iron pyrite, and then it gets replaced by this pyrophyllite, and that is a hydrated aluminum silicate. How it gets replaced, we're not exactly sure, under pressure or what, but that seems to be the most common explanation I see on the web. The explanation that I like better, because it makes more sense to me, but that doesn't mean it's even right, is that these fossils were filled with kaolin, which is a clay material. It's an aluminum silicate clay. It tends to form in tropical rainforests, which is what we had here. And as you heat it, it undergoes various changes as you drive off the water and the crystal structure changes. An interesting thing about these fossils is these are probably some of the only metamorphic fossils you have, right? So most fossils are sedimentary. They were buried and they sit there. The anthracite coal is lightly metamorphized because it's actually been changed by that pressure and heat. It is no longer quite the same structure. And people will argue whether it's metamorphic or sedimentary, but I like to say it's metamorphic. It's a little bit different and a pretty rare thing. And so that pressure and heat is what would change this to the white format that makes these ferns so good, so nice to look at and just jump off at you. You know, anybody knows what that is. Here are Neuropterus. All these Neuropterus, these large leaf ones, seem to fall in this one genus, or that's how they're classified. I kind of wonder about it because if you look at this one, it's very rounded. This one is much more pointed. I don't think that's just broken off there. If you look at these close, you can see all the veins. So pick up a magnifying glass and look at them over there when you get a chance. Here's another pair. Again, you can see the veins in that top one. The bottom one, the veins are kind of breaking down and it's starting to rip apart. But again, you got one that was rounded and one that looked like it was more pointed. It seemed to me they would be a different species, but you know, you have to have some real more definition than that to figure that out. Here's just a nice slab that's mainly Pachypterus, but down here you've got some Neuropterus with little stems holding those leaves out. But, and you'll find this when you pick up a rock, you see the fossil on it, and you say, oh, that's pretty good, or oh, that's not so good, maybe I got to get rid of it. First thing you do is turn it over because the other side might be much better. And these things are layered on layered on layered on layered. And some of the samples, you can see that. There's a Neuropterus. Looks like most of them are attached, but if you kind of look in here, you can see a little stem there. These have a terminal leaf that is a different shape than the other pinnules. So that last one, and some of them are more mitten shaped. That thumb really sticks out. This part here, some of them have even a little one over here. It's just interesting to look at and kind of see. Here's some tiny little leaflets. I mean, these guys are tiny. They're probably another species. You know, there are quite a few different species of that fall into this, or genuses, I guess I should say. But again, we're not too sure exactly how they all fit together because you can't do any genetic analysis. And this is a Sphenopterus Neuropterus. So again, Sphenopterus is the shape. So if you look at the leaf, you see the veins, you see these lobes on the leaf, kind of like an oak leaf. And if you look at it closely, you'll see all the little veins in that. I only have one of these. I've only found one in all the time I've been searching, and it's really neat. It took me a long time to figure out what it was. But almost any fossil you look in here, if you look on the rest of it, you'll see something else. I mean, they're all together. This is possibly a Neuropterus pinna without any leaves. There's the little stems where the leaflets would go. Don't know what else it would be, but I can't. I've never seen a definition of it, put that way with it saying what it was. So here we have a bunch of little roundish bumps. Could these be seed ferns or seed fern seeds? They definitely could. There's not a lot of round shapes in these. It's not like collecting along the bay. But then you look at these and you say, oh yeah, those are seed fern seeds. And if you look at that one, it's over an inch tall. And so they definitely have a structure. There's all different kinds of them. They're pretty neat to find because these are some of the first seed plants. Gymnosperms, because the angiosperms have not evolved for at least another 50 million years, maybe 150. Miscellaneous fossils. Finish this up. I've got Sphenophyllum. People say it resembles broom straw. Well, who knows what broom straw is? But it's a stalk with these leaves radiating out, kind of like the annularia. But the leaves are broader and tend to be wedge-shaped. They can be square on the outside. They can be rounded. They can even be ragged. So there's different kinds of them. I've got a bunch of them here. At the end of that stalk, the Sphenophyllum grew as a low shrub or a vine. So it didn't really have much structure to hold it up. But at the tip of it, it would have a cone that would be a sporophyte. And they call that a Baumanites, was the original name for it. But it's really where the spores came out on the Sphenophyllum. This, I don't know what it is. I have two of them, very similar. Could it be the bud on the end of a Calamites? Some of these have a little cone on the end. That'd be my guess, but I really don't know, and I haven't found any place. There's the other one that describes it, but they're neat. This is the Lepidophylites, the lepidendron foliage that we talked about. So when the tree was growing as a straight trunk, it would have almost grass-like leaves, and these could be 1 foot, 2 foot, maybe 3 foot long. Fairly narrow because it only had one single vein down the middle. It didn't have any veins out to the edge. When the tree matured, it got these needle-like structures, and they kind of all come off right here. This isn't the greatest picture. See it a little better on the screen. But they come off right here, and they're all separate needles. But at the same time, the chordates were evolving, the first conifers, or the ancestors of the conifers, with a needle-like leaf. So could that be a chordate that got washed into the swamp? I don't know. You would think that Lepidophylites, the leaves of the lepidodendron, would be fairly common, though. And I do not see these a lot. And this is a very interesting one. It reminds me of a skunk cabbage spathe, the flower covering, because it comes up here and then it comes over. And then the other side of it comes down here and it comes around. I have no idea what that is. I have not found anything like it. I have to go through all my books again and see if I can find something like that. But it's just, is it a deformed leaf, a leaf that was starting to grow or something? But I don't really know. So at this point, feel free to look at the fossils. Feel free to ask questions. I got giveaways to everybody in here. You can take anything off this table. Please don't take those ones over there. We also have a copy of Fossil Collecting in the Mid-Atlantic States for the book sale. It's going to be raffled off right here. If you want to bid on it, feel free. If you want to bid in the chat, you can bid. It's a great book, Jasper Burns. It's got 30 some odd fossil sites, some of which 48. Some of them no longer exist, but it's got great little pictures in it of the different fossils. So it's a great book to help you identify things. And he tells you what's there and what you might find and all that. It's a great book. So I got a sheet up here. If you want to put your name and a bid on it, we'll auction it off. Any questions? I do not know of any leaf fossils in southern Pennsylvania. That far up, and that's about the start of where the fields start, the anthracite fields. Most of these lands are old strip mines. On the table underneath the samples, I have some maps from the Geologic Society that lay out the coal in the various places. Happens to be a Bear Valley, and who owns the mines and everything. It's just kind of a neat little thing. A lot of those have been bought up by a company called Reading Anthracite. People used to go onto Reading Anthracite land, collect fossils, and sell them. People used to lead trips and charge $75 for you to take you in for a day to collect fossils on land they didn't own. So Reading Anthracite shut down the coal collecting. If they do, they have a little round plaque along the road. Usually it says famous Reading or famous Reading Outdoors. It's the name of the company now. And you can buy a yearly membership for $75, it used to be. And you can ride your quad bike or your motorcycle through the strip mines. But there's a lot of other strip mines, particularly as you go further north in that southern plant batch, which is all owned by Reading now, that are just strip mines that are out there. You drive down some of these rural roads, you see this hill, and it will have very little vegetation or very thin vegetation on it. It's a good chance it's an old stripping pile, a spoil pile, a culm pile. There was on the south side of Shamokin, or north side of Shamokin, I guess, there's this huge pile because there's a big underground mine there. And when they pull the coal out, they always get shale in it, and they got to get rid of it, so they just dump it. And for a while, they claimed they had the biggest spoil pile on the earth. And they stopped claiming that, in the 60s because it was no longer a positive thing. Other questions? Any online? Bid on the book. If you're here, grab a fossil, look at the fossils. Feel free to ask questions. It's been a pleasure. Thank you.